In this video, we will go over more reactions of aldehydes and ketones, including thioacetals and desulfurization, hydrogen nucleophiles, also known as reduction, carbon nucleophiles, and that includes Grignard reagents and cyanohydrin formation. We'll go over the Wittig reaction and the Baeyer-Villiger oxidation. Thioacetals are almost exactly like regular acetals, except instead of having an oxygen, the nucleophile is going to be a sulfur atom. Now, sulfur is just below oxygen on the periodic table, so they act very much the same. So this mechanism is going to be exactly the same as the acetal formation mechanism that we saw in the previous video. Now, one difference that we have with thioacetals versus regular acetals is that in the presence of a ketone, the thioacetal formation does not involve removing water, and that's because the thioacetal formation is favorable. The reason being is that sulfur is a stronger nucleophile than oxygen, so it's going to attack the carbonyl carbon a lot faster than an oxygen. Thioacetals are most useful as reducing agents in a process called desulfurization. With desulfurization, we can start with a thioacetal and treat it with a reagent called Raney nickel. And what this is going to do is it's going to remove the thioacetal portion and replace it with two hydrogens. So essentially, we're reducing the carbonyl carbon. It's just another way of getting rid of a carbonyl of an aldehyde or ketone. Hydrogens are also capable of acting as nucleophiles, and we've seen these types of reactions before in the alcohols chapter. So there's two types of reagents where we see hydrogens acting as nucleophiles. We have lithium aluminum hydride, or LAH, which is this molecule here, and then we have sodium borohydride, which is this one here. Both of these reagents are capable of taking aldehydes or ketones and reducing them down to alcohols. We can take a look at the mechanism. Again, this is going to be a review from the alcohols chapter. So just as we've seen with all of the mechanisms in this chapter, we're going to have a nucleophilic attack to the carbonyl carbon. Let's go ahead and take a look at the mechanism using lithium aluminum hydride. Now the lithium is just a counter ion to balance the negative charge on the aluminum. So in this mechanism, the aluminum is going to kick off one of the hydrogens as well as its electrons. So anytime we have a hydrogen with electrons, it's called a hydride ion. Now, as the hydrogen attacks, it's going to kick the electrons up onto the oxygen. So we get an intermediate where we have a negative charge on the oxygen. We've just added a hydrogen to the carbonyl carbon. Then our last step is going to be putting this molecule in the presence of a protic solvent, such as water. And this can really be any sort of protic solvent, including water or methanol or ethanol. In my example, I'm just showing water as our proton source. So the oxygen will go and take the H from our protic solvent. We will protonate the oxygen and create an alcohol. Carbons are known to act as nucleophiles as well, and we've seen this before with Grignard reagents. So a Grignard reagent is when we have an R group, some sort of carbon group, attached to magnesium bromide. Now, in reality, even though we have this bond being shared between the R group and magnesium, really the electrons are more so towards the R group or towards the carbon atom, and the magnesium bromide is just stabilizing it with a positive charge. So with our Grignard reagents, this is capable of acting as the nucleophile. So in the presence of an aldehyde or ketone, the electrons can act as a nucleophile and attack the carbon of the carbonyl, kicking the electrons up onto oxygen. Now we've seen this mechanism before, again in the alcohols chapter, because Grignards are one of the ways to make alcohols. Now this allows us to form a new carbon-carbon bond between the R group and the carbonyl carbon. then the last step of our mechanism is to protonate the oxygen with a protic solvent such as water. So grignards are one ways that we can take aldehydes or ketones and make alcohols. Carbons can also act as nucleophiles with cyanohydrin formation. With cyanohydrins, we start with an aldehyde or ketone, and we treat it with potassium cyanide and HCN. Ultimately, we're going to create a product that has a cyano group as well as an alcohol, and this functional group is known as a cyanohydrin. Now, as for the mechanism is going to be very similar to the types of mechanisms we've seen so far. So we have our aldehyde or ketone, again with our electrophilic carbon atom. Now the potassium cyanide contains a cyanide ion, and a cyanide ion has the lone pair on the carbon with a negative charge, so it's a very good nucleophile. Now this is going to come in and attack the carbon, kicking the electrons up onto oxygen. Again, we have an oxygen with a negative charge, and we formed a bond between the carbon of the cyano group as well as the carbonyl. So technically this is a carbon-carbon bond forming reaction because we do add an additional carbon to the molecule. The last step, the HCN is going to act as a proton source. The oxygen will take the H, giving the electrons, and create a new cyanide ion. And we finish with our cyanohydrin. Cyanohydrins are most useful in synthesis, and we're actually going to be seeing these reactions later on when we talk about these different functional groups. So we can take a cyanohydrin and treat it with LAH as well as water. And the LAH is going to provide hydrogen atoms across both pi bonds of the cyano group. Ultimately, we're going to end up with a CH2 and an NH2, so we turn the cyano group into an amine. So we can actually use cyanohydrins to synthesize amines. So we will see this reaction again with our amines chapter. We can also take a cyanohydrin and treat it with H3O+, and we can oxidize the cyano group into a carboxylic acid. So this is one way to form a carboxylic acid, which we will see in the next chapter. The last reaction where we will see carbon acting as the nucleophile is the Wittig reaction. The Wittig reaction involves a carbonyl from an aldehyde or ketone plus a phosphorus ylide, and we'll take a look at what that is in just a bit. And we can create a mono, di, or tri-substituted alkene as the result of this reaction. So first we'll go ahead and take a look at how we prepare the Wittig reagent, which is also known as the phosphorus ylide. Now the phosphorus ylide preparation begins with a molecule called triphenylphosphine, which is a phosphorus with 3 benzene rings attached. Now the triphenylphosphine is going to react with an alkyl halide. And this is going to be a standard SN2 mechanism. So the lone pair on the phosphorus will go and attack the carbon containing our good leaving group and kick off our iodide ion as our leaving group. So since this is an SN2 mechanism, we are limited to using methyl primary or possibly secondary alkyl halides. Now, after the phosphorus has attacked, we have a bond between the phosphorus and the carbon that originally contained our leaving group, and that carbon was also attached to another methyl group. Now the phosphorus, because it gave up some of its electrons, now has a positive charge. So at this point, we're going to treat this molecule with a super strong base called butyl lithium. And butyl lithium is a 4-carbon chain with a negative charge on the end carbon. And this negative charge is stabilized by a positively charged lithium. So this butyl lithium is extremely strong. Now the reason that we need to use a strong base in this case is because we're actually going to be taking one of the protons from the carbon atoms. Now this proton is not very acidic, so you need to have an extra strong base in order to remove it. But once we remove this H and give the electrons to the carbon atom, we're actually going to create our Wittig reagent. So we still have our phosphorus bound to the 3 benzene rings. The phosphorus is still positively charged. The carbon now has a lone pair, which is going to make it negatively charged. So overall, this Wittig reagent is neutral because the positive and negative charge balance each other out. We also have resonance occur because the electrons from the carbon can be donated to the phosphorus. Now phosphorus is capable of taking on more than 8 electrons, and by taking these extra electrons, it's actually going to restore its charge to neutral. So these resonance structures exist simultaneously with one another, and this is known as the Wittig reagent. So on the next slide, we'll see how the Wittig reagent will react with an aldehyde or ketone to form our alkenes. So I'm going to react our Wittig reagent with this ketone here. And I'm going to draw the charged version of the Wittig reagent so we can see how the charges play a role in the mechanism. So we have our negative charge on carbon. This is a very strong nucleophile right here. We also have a positive charge on the phosphorus. Now on our ketone, and we would also see this on an aldehyde, we have a slightly positive charge for our carbonyl carbon and a slightly negative charge on our oxygen. So in the first step of the mechanism, the lone pair from the carbon are going to come over and attack the slightly positively charged carbonyl carbon. Now at the same time, the pi electrons are going to come over and attack the positively charged phosphorus. Now we're going to form an intermediate between all 4 atoms involved. So we have the carbon of our Wittig reagent still attached to the methyl and the H. We have the oxygen now attached to the phosphorus, and the phosphorus is still attached to the carbon. Now because the carbon gave up its electrons, it is now neutral, and because electrons now came to the phosphorus now has the appropriate number of electrons and is also neutral. So we have a neutral intermediate here. Now our next step is we're going to be forming our alkene. So the electrons between the phosphorus and carbon are going to move over and form a double bond between the carbon of the Wittig reagent and the carbonyl carbon. Then the electrons between the oxygen and carbon are also going to break, and they're going to form a double bond between the oxygen and the phosphorus. So we form this molecule as a byproduct. I'm going to go ahead and put it in parentheses. But most importantly is we have formed an alkene. And in this case, we have a tri-substituted alkene. If the aldehyde or ketone that we start with in the Wittig reaction is asymmetrical, there's a chance that we can form two different types of alkenes, either the E or the Z version. Now, for the most part, Z alkenes are usually favored in the Wittig reaction. However, E alkenes are favored if the Wittig reagent contains an electron withdrawing group. So for example, we're starting out with this asymmetrical ketone here, and we're treating it with this Wittig reagent. Now the Wittig reagent contains an H on one side and a methyl group on the other side. So in the end, we're going to end up with the Z product, meaning the bulky groups that are attached to each one of the carbons of the alkenes are on the same side. So for our top carbon, the methyl is our bulkiest group between the methyl and the H. On the bottom carbon, we have an ethyl group versus a methyl group, and so our ethyl group is the highest priority. So since these two are on the same side, it makes them the Z product. However, if the Wittig reagent contains an electron withdrawing group directly attached to it, so in this example, we have a carbonyl, an ester functional group. This is an electron withdrawing group. Electron withdrawing groups actually promote the formation of the E product. So in this case, focusing on the two carbons of the alkene, we have our higher priority group and our higher priority group on opposite sides, so we end up with the E product. Now I just wanted to introduce this concept. For the purposes of our class, we will always be starting with a symmetrical ketone or aldehyde, and so you don't need to worry about which one of these products will form. The last reaction we're going to be talking about is the Baeyer-Villiger oxidation. In this reaction, we can start with an aldehyde or ketone. In this example, I'm going to start with a ketone. Now I'm going to treat the ketone with peroxy acid. We've seen this reagent before with the formation of epoxides. Ultimately, ketones will be turned into esters. So we're actually going to be breaking the bond between the R group and the carbon. So this is technically a carbon-carbon breaking reaction. Up until this point, the only other carbon-carbon breaking reaction we've learned has been ozonolysis. So now we have a new type of reaction that we can use in synthesis problems. So let's go ahead and go through the mechanism. Now in this mechanism, the oxygen of the peroxy acid is going to act as our nucleophile. So I will go ahead and draw out peroxy acid. It contains a carbonyl as well as an oxygen attached to another oxygen. I'm going to go ahead and label this one blue. And that oxygen is attached to an H. So our blue oxygen is going to be the one acting as the nucleophile. And just as we've seen in all of our other mechanisms, we have the electrons come up and attack the carbonyl carbon and kicking the electrons up onto oxygen. Okay, so for our next step, we're going to be involving a lot of atoms of this intermediate. Now the oxygen of the peroxy acid, of the carbonyl of the peroxy acid, is going to use its lone pairs and take the extra H from our blue oxygen. Now the blue oxygen currently has a positive charge, so we're going to take that H and we're going to give the electrons back to the blue oxygen. Now this step occurs very readily because we have a 5-membered transition state. We're involving 1, 2, 3, 4 5 atoms. So this forms a very nice ring and allows it to work with itself. So we'll give the electrons to the oxygen and form another intermediate. Oops, I lost the R groups. Let me just draw on the R's. Now, we have a negative charge on this oxygen here. We have a positive charge on this one over here. So overall, we're going to try and get rid of these charges. So we're going to start with the source of the electrons, the negative charge. What's going to happen is these electrons are going to come down and they're going to start to reform the carbonyl, the C double bond O, between the carbon attached to the blue oxygen. Now this is going to cause a migration of one of the R groups. So one of the R groups, as well as the electrons, are actually going to move over and attach themselves to the oxygen atom. I'll go ahead and label these electrons red so we can see how this migration is going to work. So the red electrons will come over and form a bond with the blue oxygen. Now that's going to cause the electrons between the two oxygens to break. Now this is a very easily broken bond. It's very weak, so this will break fairly easily. Now these electrons will shift over to form a double bond, and then we'll kick the electrons of the original double bond up onto oxygen to get rid of that positive charge. So this step involves the migration of the alkyl group, and this is how we actually break the bond between the R group and the carbon. So at the end of this step, we're going to be left with an ester where the red R group is now attached to the blue oxygen. We will also be left with a side product of a carboxylic acid that came from our original peroxy acid. I'll go ahead and put this in parentheses because we don't really care about it. But that is our mechanism for our Baeyer-Villiger oxidation. When the ketone is actually incorporated into a ring, this is known as a cyclic ketone, the result of this Baeyer-Villiger oxidation is the oxygen is actually inserted into the ring and expands it by one atom. Now this type of structure where we have an ester functional group incorporated into a ring is known as a lactone. So this is the type of structure we will see as a result of a cyclic ketone. Now when we are working with asymmetrical ketones or aldehydes, the O is inserted based on the migratory aptitude of the different groups that are attached to the carbonyl. So this is an example of the order of migratory aptitude. And migratory aptitude is just looking at how willing is this group to undergo that migration step and shift over to be attached to the oxygen. So methyl groups are the least likely or have the lowest migratory aptitude. So those are going to be the ones that shift last. Then it goes to a primary group. A benzene ring or a secondary carbon will have a greater migratory aptitude, then tertiary, and finally hydrogen. So with this order, we see increasing migratory aptitude. So on the next slide, let's look at a couple of practice problems to see how we can use this information to predict the product of a Baeyer-Villiger oxidation. So let's go ahead and predict the products of these two molecules. So first we're starting with an asymmetrical ketone. And what we're going to do is we're going to focus on the carbons directly connected to the ketone. So we have this carbon here and this carbon here. Now, the carbon on the left is bound to two other carbons. We ignored the carbonyl carbon. So that's going to make this a secondary carbon. The one attached here is simply a methyl group. Now, as far as our migratory aptitude, a secondary carbon has a greater migratory aptitude than a methyl group. So that means the oxygen is going to be inserted here. Okay, so we'll go ahead and draw our product. Now the methyl group is going to stay put. We're now going to have an oxygen, and then we have our three carbons attached to that oxygen. So you always want to make sure to count your carbons and make sure you don't lose a carbon in the process of this reaction. Let's go ahead and try our second example. So in our second example, we're going to focus on this aldehyde. So we have the aldehyde attached to a carbon as well as an H. So this carbon is attached to one other carbon, again ignoring the carbonyl carbon. So this is going to make it primary. The H is simply the H. Now the H has the highest migratory aptitude, so that means our oxygen is going to be inserted here. So let's go ahead and draw our product. So aldehydes actually form carboxylic acids as a result of the Baeyer-Villiger oxidation. And that's always going to be the case because the H is always going to have the highest migratory aptitude.